This is 6.3 homework, more concepts of probability. So in this assignment, we're going to talk about some new terms, mutually exclusive versus non-mutually exclusive, and then later on we'll talk about independent versus dependent events. Okay, mutually exclusive versus non-mutually exclusive. It's a real simple idea. Mutually exclusive, what this means, if you think of your sample space, so let's think of this as our sample space, and you have mutually exclusive events, when you draw them, you have some events A, and then when you draw the events B, you'll see there's no overlap between A or B. And so we call these A and B mutually exclusive if the picture looks like this. Non-mutually exclusive, you get some overlap. So if we draw another picture here, the idea would be here's event A, and then here's event B, and you get some overlap, something in between. So let's look at the first example and decide if these are examples of mutually exclusive or non-mutually exclusive events. So I'm going to roll a die, and event A is going to be get an even number. Event B will be get it less than a 3. All right, so the idea of an even number, of course, A has 2, 4, and 6. Right, so this is my A. And then my B, well, less than 3, so that's 1 or 2. Right? Those are two numbers on the die that are less than 3. And you see that these cannot be mutually exclusive because there's an overlap. Right? 2 is in both of them. So this is an example of non-mutually exclusive events. And number 2, we roll a die and we get a prime number, which is 2, 3, or 5. Or get an odd number, okay? So here, this is our event A, and it's 2, 3, or 5. And then here, this is our event B, right? So this was A, and this is going to be B. And an odd number, which would be, what, 1, 3, or 5. All right, so is there some overlap? Certainly there's some overlap, right? Prime numbers 3 and 5 are also odd. So these are, again, an example of non-mutually exclusive events. All right, select a student in your class. So the student has blonde hair, A, or the student has blue eyes, B. So again, we have to ask ourselves the question, will these two sets overlap? A is a set of people with blonde hair, B is a set of people with blue eyes. And obviously there's going to be some overlap because the overlap says I have a blonde hair person that also has blue eyes, and that's quite probable. So I would say these are probably non-mutually exclusive events. There's a Y up there. Finally, part D, select any college level course. It is a college mathematics course, so that's my event A. I select a college mathematics course, or it is an English course, B. Right? So when I think of this, I have event A, I select a college mathematics course, right? So it could be college mathematics, college algebra, calculus, pre-calc, whatever. Or I select an English course, so it'd be like freshman English 1, freshman English 2, early British literature, something else. Is there going to be any overlap? And I'd say no, because there is not a course that is both mathematics and English. They're separate things. So this is an example of two events that are mutually exclusive. All right, when I draw the picture, the set of things, so here's my sample space S, which is a set of all courses offered. And then here A would be the set of all mathematics courses, so I'd list them all in here. Set B would be the set of all English courses, so I just list them all here. And you'd see there's no overlap. There's no course that is both a mathematics and an English course. Select a registered voter. The voter is registered as Republican, or the voter is registered as Democrat. All right, so here I have A, registered as Republican, and then here registered as Democrat would be my B. And this is also an example of two events which are mutually exclusive. because you do not have the option of registering for both. So you think, okay, well, here are the Republicans registered as Republicans, here are the registered as Democrats. Of course, you have all the people registered as whatever, independents, or Republicans or Democrats, but you see there's no overlap. You can't be both a Republican and a Democrat as registered. Okay, so there's some examples of non-mutually exclusive and mutually exclusive events. Let's use this because what we have, the idea and why this stuff is kind of important, is if we're trying to figure out the probability that A occurs or, for the union, B, so or B occurs, what we can do is we can say this is the probability of A, right, plus the probability of B. If they're mutually exclusive, we're done. But if they're not, we have to remember to subtract off their intersection, probability of A intersect B. Right? This happens, and you can see this from the picture. If you compute the probability of A, right, basically you compute this probability plus the probability of B, so you compute this probability. But you see when you count these, you actually count the intersection not once, but twice. So you have to take it off once so you don't double count it. Right. In the case of mutually exclusive events, there's no intersection, so you don't even need this term. Right. The probability that A and B occur is actually 0 because there is no intersection. All right, so now we want to determine the following probabilities by filling in the various parts below. All right, so just like we did up here, we saw that rolling a die and getting an even number or something less than 3, that this was actually non-mutually exclusive. So let's show that. So getting an even number, this is going to be our A. And so an even number would be 2, 4, or 6. So I'm actually going to write 4 and 6 here, and 2 here because B is get a number less than 3. So I'll have 1 and 2 and B. And so A, I can write here if you want. This is just the number of things, so 2, 4, and 6. And then B, actually I should have probably done this first, is 1 and 2, right? Numbers less than 3. And then I can fill this in. So you can see 4 and 6 are in A, but 2 is in A and B, and then 1 is in A, just like we did in the last section, right? A intersect B is just equal to a 2. The number of things in A is 3. The number of things in B is 2. The number of things in A intersect B is just one thing. And so to compute the probability of A union B, which means the probability that I roll an even number or I roll a number that's less than 3 would be equal to, I can break it down and say P of A plus P of B, and then take away the intersection, P of A intersect B. So that's equal to the number of things in A divided by my total numbers of things in my sample space. So how many things are in A? I said 3. And my sample space, where there's 6 possible outcomes, so 3, 6, plus the number of things in B, so that's 2, right, then divided by 6. Right, so I have 2 things in B, divided by 6, and then take off their intersection, right? So the number of things in the intersection of A and B, which is just 1, right, divided by 6. And so I get 3 plus 2, which is 5, minus a 1, which is 4, so 4 over 6, which equals 2/3, or we could write 67%. All right, so if I roll the die 3 times, I would expect 2 of those times I get either an even number or I get a number that's less than 3. Let's look at the next one. So the next one I draw from a 52 card deck. And I want to figure out I get an even number or a face card, Jack, Queen, King, and Ace. And let's fill out A and B first. So for A, I get an even number. Let's just write, so I have even numbers, right, which is what? Let's see. This is equal to, so all even numbers, and let's write down a better description here. So the set of all even numbers, which is equal to the set of, right, you have 2, 4, 6, 8, and 10. And remember, you have these in hearts, diamonds, right? So hearts, diamonds, so in hearts, diamonds, clubs, and spades. All right, so what does a spade look like? Oh, like this. something like that. So spades. All right, so I have 2, 4, 6, 8, 10, and hearts, diamonds, clubs, and spades. So there's a lot of things listed here. And then in B, I get a face card, Jack, Queen, King, or Ace. So again, on here for my B, right, I have a face card. And I could probably list these a little bit better. So let's think about how I could list these a little bit better. So this is equal to what? Let's rewrite that. I don't like the way that looks. So I have a face card. So face card. And that's equal to, okay, so what do we have? We have Jack, Queen, King, and Ace, right? And again, we have these in hearts, diamonds, clubs, and spades. All right, so let's put these into my A and B over here. So what I have for even numbers, right, there are no face cards here, so this is going to be my A. So I just write down the even numbers, and so to save space, I'm just going to write down 2, 4, 6, 8, and 10. And then below this, I'm going to write hearts, or hearts, diamonds, and clubs, and then spades. And then for B, these are all the face cards. So I have Jack, Queen, King, and Ace. And again, these are all in hearts, right? So I have a Jack of Hearts, Queen of Hearts, King of Hearts, Ace of Hearts. Same thing with diamonds. So I have these diamonds and clubs and spades. So right below it, you know, in hearts, diamonds, clubs, and spades. And the thing you want to see here is that there's nothing in this intersection, right? Because face cards aren't considered even numbers, nor are even numbers considered face cards. So in the intersection, if we want to be fancy, we can just write this symbol, the empty set, a 0 with a line through it. Okay, the number of things in A. So now I have to think a little bit. So I have 2, 4, 6, 8, and 10. So I have basically 5 cards, right? So like 5 hearts, 5 diamonds, 5 clubs, 5 spades for a total of 20 things. And if you want, you can list them all out. It just takes a while. And number of things in B, okay, well, I have 4 hearts, 4 diamonds, 4 clubs, and 4 spades. So that's 4 times 4, basically. So I have 16 things there. And in the intersection, I have 0 things. So this is an example of 2 events which are mutually exclusive. So this is just going to be the probability of A plus the probability of B. But notice, if you say minus probability of A intersects B, you'll be just fine. So we might as well just do it. Whenever we're computing the union, we can just think, oh, take the probability of A plus the probability of B minus the probability of the intersection. And so the probability of A, well, it's a number of things in A, so that's 20, divided by the total number of things in my sample space, which are just 52 cards, plus the probability of B. I have 16 things in B, divided by, again, 52 cards. And of course, minus how many things are in the intersection, 0 divided by 52. That's why we can leave it on. We can put it there or leave it off. And so 20 plus 16 is 36 divided by 52, which reduces to 18 over 26, which we can continue to reduce to 9 over 13. All right, so if I draw a card 13 times, I'd expect out of those 13, 9 of them to be either an even number or a face card, Jack, Queen, King, or Ace. You can crunch this on your calculator and see that 9 over 13 is about 69%. All right, let's flip it over and look at the back side. So on the back side now, we're going to start talking about independent versus dependent events. And so the idea is that if we know a certain event like B has occurred, will that now affect the probability that A is going to occur? So like in this first example, tossing a coin and drawing a card from a deck. Are somehow these events intertwined? If I toss a coin, say I throw heads, will that affect me drawing let's say an ace from a deck of cards? Obviously not. So these are examples. This is an example of what we'd call independent events. All right, we have tossing a coin, and then drawing a card from a deck. So independent events. Next one, drawing a ball from an urn, not replacing it, and then drawing a second ball. So this is actually an example of dependent events, and they're dependent because you're not replacing the ball after the first event. So here's the first event. You draw a ball from the urn, but you don't replace it, and the next event is you draw a second ball. So this is an example of two events which are dependent on each other. They're dependent because, in a sense, you've reduced the overall size of the sample space because you didn't replace the ball. So drawing a card, replacing it, and then drawing another card. Now, this is an example of independent events. Okay, so you draw a card, but then you replace it, and then you draw another card. Right, so by drawing the first card, it's not going to affect the outcome of the second because you replaced it. Up here, though, you did not replace. So I made these two dependent events. Whereas if you replace it, you get independent events. Okay, smoking excessively and having lung cancer. All right, so event A is that you smoke basically, and B is that you have lung cancer. Are these dependent or independent events? I would argue that they're dependent events, but some people may argue that they're independent. I argue that they're dependent because I think if you smoke excessively, right, that's going to change the probability of you having lung cancer. And that's really the idea of independence versus dependent, right? If you assume one occurs, does that affect the outcome, the probability of the other, right? So if I assume that you smoke excessively, I think that the probability that you have lung cancer will actually increase because I think there's some sort of correlation there between smoking and lung cancer. Okay, let's take a look at the following. And in number 4, notice it says determine the probabilities of the following independent events. Okay, so I'm telling you now that these are all independent. You don't have to decide for yourself. I'm telling you they are. And the reason why we want to work with this is because if two events are independent, it's easy to figure out the probability, in a sense, of A intersect B, the probability that A occurs and B occurs. Because if they're independent, we have this formula, which we'll learn more about when we come back from break, that P of A intersect B is P of A times P of B. All right, so in part A, let's look at it. We flip a coin and draw from a 52-card deck. We want to figure out that probability that we get a tail on the event is get a tail, so that's my A. And my B is draw a heart. Okay, so let's write down A. All right, event A is we get a tail, so you just have T. And then event B is that we get a heart. Now, there are lots of hearts. There's actually 13 hearts. So on here you can draw, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a 10. These are all hearts. Or you could have a jack, a queen, a king, or an ace, right, in hearts. And you can count them up: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards. And we want to figure out the probability of A intersect B. So since they're independent, we can use this formula here. Right, so this should be equal to, you're told they're independent, so P of A times P of B. Right. Oftentimes it's hard to decide whether two events are dependent or independent unless you really understand the situation, like the smoking excessively or having lung cancer. One might argue that these are independent events, and so you might have to have some data to try to figure out if they're independent or dependent. All right, so since I'm assuming this, it's easy though. I figure out the probability of A, which is equal to the number of things in A divided by the number of things in the sample space, and here we're flipping a coin, so that's just 2, times the number of things in B, which we said was 13, divided by the number of things in its sample space, which is a 52-card deck, so 52 things, and that's equal to then 13 divided by 104. And so this is our answer. So if I do this 104 times, I flip a coin and draw a card from a 52-card deck, I would expect that 13 of those times I would get a tail and then draw a heart. And I can actually figure out this percentage on my calculator by taking 13 and divided by 104, which should be close to kind of 13%, so or 12.5% of the time. Okay, on the next one, what are we doing? So on this next one, we're drawing a ball from a urn that has 3 red balls, 3 blue balls, 4 green balls, and we want to figure out here we have 2 events. We get a green ball, I replace it, and then getting a red ball. Okay, so event A is what? Just getting a green ball. All right, so we have a green ball here on the first draw. And then on the second draw, what do we have? Well, we have getting a red ball. Right? So we have a green ball and we have a red ball. And so the probability that A and B occur would be equal to, since I already told you these are independent events, we know it's P of A times P of B. Again, it's important that we're assuming that these are independent. I'm telling you they are, so that's why I can use this formula. If they were dependent, I cannot use this. And so this is equal to, well, what's the probability of A occurring? Well, I have a green ball. All right, so how many green balls do I have? I have 4 green balls, so the number of things in here in A is actually 4. There are 4 green balls, so I have actually 4 balls in there. And so I have 4 divided by the total number of balls, right? The total number of things in my sample space. So 3 plus 3, that's 6, plus 4 is 10. So 4/10 as a probability of drawing a green ball, times then the probability of drawing a red ball. So how many red balls are there? There are actually 3 red balls, right? There are 4 green balls, 3 red balls, so it's 3 divided by 10. Notice I did replace it, so it's still 10 on the bottom. And so this is equal to 4 times 3, which is 12, divided by 10 times 10, which is 100. And this is equal to the 2's cancel, so 6 over 50. Oh, the 2's cancel again, so 3 over 25. And so if I do this 25 times, I draw one ball and I draw another, I would expect 3 of those times that I would draw a green and then get a red. All right, so or 12% of the time. All right, so on the next one then, what do we have? All right, so now we're going to draw from a 52 card deck, and we have getting a face card, replacing it, and then getting an ace. And so for part A, I have a face card. All right, remember in here, a face card, what is it? It's a jack, a queen, a king, or an ace, and in 4 different suits, right? So it could be a heart, it could be a diamond, a club, or it could be a spade. There are 4 different suits there, and then B is getting an ace. All right, so I have an ace, which this is equal to, we can write these out, you have ace of hearts, ace of diamonds, ace of clubs, ace of spades. And we want to figure out the probability of A intersect B, whether it be P of A times P of B. All right, so the number of things in A, you count them up, 1, 2, 3, 4, and you have 4 suits, okay? So you have basically 4 hearts, 4 diamonds, 4 clubs, and 4 spades. And so that should give me 16 things in A, divided by 52 cards. So that's the probability of A occurring, times the probability of B occurring. Well, the number of things in B, we just said was 4, right? And we divide by the number of things again in the sample space, which is still 52 because we replaced the card, so you have 52. And so this is then equal to 16 times 4. Right? Well, I can do that on my calculator. So 16 times 4, which equals 64, divided by, and then 52 times 52, which equals 2,704. And obviously you can cancel off some 2's here, so I get 32 divided by, and I can divide this by 2. Let's see what it's equal to, so 1,352. I can divide this by 2 again, so 16, divide that by 2. So 676, and keep going. So divide by 2 again, I get 8. I divide by 2, 338. Just keep going until it's not even anymore, basically, right? So divide by 2, so I get 4 over 169. Only thing that goes in 4 are 2's, and 169 is not even, so we're good. So my answer is 4 divided by 169. So if I do this 169 times, I draw a card from a deck twice, replacing it in between. I'd expect 4 of those times I would get a face card, and then I would get an ace to follow. I could actually, and I can compute this percentage too, so 4 divided by 169 is equal to, and this is about, what, 2.4%, so or 2.4% of the time. Let's finish up with this last one, part D. So on part D, I roll a die 3 times. Get an even number on the first roll, that's going to be my A. Get an odd number on the second roll, that's going to be my B. And then get a 3 on the last roll. All right, so let's write these down. A, even number on the first row, so that's 2, 4, 6. Odd number on the second roll, so that's 1. I could do 1, 3, or 5. All right, there's only 6 numbers to choose from. And then a 3 on the last roll, so that's 3. So 3. And so, assuming these are all independent, the point of this problem is to show you that you can generalize this. So if you had to generalize it, you could guess P of A intersect B was P of A times P of B. P of A intersect B intersect C would be P of A times P of B times P of C. And so this will be equal to the number of things in A, right? P of A is the number of things in A, divided by the number of things in your sample space, so that's a 6, times P of B, which is also, there's 3 things in there, so 3 over 6, times the number of things in C, which is 1, right, divided by the number of things in sample space, which is 6. And so on here, I get on top 9, I can do in my head. 6 cubed, I don't do too often, so let's do it. So 6 times 6 times 6 is equal to 216. Right. And to see if this reduces, I can see if a 3 goes into 216, so divide this by 3. And I get 72, so it does, so 3 divided by 72. And I can check if 3 goes into 72, and it does, so I get this to be 1 over 24. Or, I can figure out the percentage on here, about 4.2% of the time. All right, but my answer is 1 over 24. All right, so if I roll a die 3 times, and I do this 24 times, I would expect that at least one of those times I should get an even number in the first roll, an odd number in the second, and a 3 in the last roll. Will I actually get that? Maybe, maybe not. But if I do it a lot of times, I would expect that 42% of the time this actually occurs.